Welcome to Part 16 of Applied Chemistry, focusing on phase rule and phase diagrams. Gibbs phase rule is a thermodynamic concept proposed by J. Willard Gibbs. It describes how many variables in a system can change without disrupting its equilibrium. This rule is essential in thermodynamics and phase diagrams, giving insights into the behavior of chemical systems across temperature, pressure, and composition variations. The formula for Gibbs phase rule is F equals C minus P plus 2,
where
F is the degrees of freedom, representing the number of variables that can independently change without impacting equilibrium. C is the number of components, the minimal independent substances that define the system's composition. P is the number of phases, physically distinct, homogeneous parts of the system. This formula helps us understand the constraints and flexibility in phase behavior across different systems. In phase rule analysis, understanding key terms is crucial. Phase, a physically distinct, mechanically separable part, such as a solid, liquid, or gas. Component, the minimal set of chemically independent substances defining each phase's composition. Degrees of freedom, variables that can change independently without altering the phase equilibrium. Invariant system, a system with 0 degrees of freedom, meaning no variables can adjust without disturbing equilibrium. One-component systems like water and sulfur showcase phase behaviors of single chemical substances. In these systems, a phase diagram demonstrates how phases change under specific conditions, showing solid, liquid, and vapor states and key transition points, such as triple points and critical points. The water system phase diagram highlights the behavior of water as it transitions between solid, liquid, and gas. Important points include triple point at 0.0098 degrees Celsius and 4.58 millimeters of mercury. All three phases coexist in equilibrium, with no freedom to change independently. Critical point at 374 degrees Celsius and 218 atm. Water reaches a state where liquid and vapor are indistinguishable, marking the end of the liquid-vapor boundary. Phase boundaries. These represent conditions where two phases coexist, such as the boundary between ice and liquid or water and vapor. Here's what the phase diagram for water system looks like. This will help you get better understanding of the concept. Applying Gibbs phase rule to water's phase diagram. At the triple point, C equals 1, P equals 3, F equals 0, indicating no flexibility in temperature or pressure. On phase boundaries, for example, along the ice-water line, C equals 1, P equals 2, F equals 1, meaning either pressure or temperature can vary while maintaining equilibrium. The sulfur system is a unique one-component system because sulfur exists in two solid forms, rhombic and monoclinic, along with its liquid and vapor states. The phase diagram shows transitions between these states and includes two triple points where specific phase combinations coexist. In sulfur's phase diagram, there are two, where either rhombic, monoclinic, and vapor phases coexist, or monoclinic, liquid, and vapor phases coexist. Rhombic sulfur transforms into monoclinic sulfur around 96 degrees Celsius at 1 atm. Beyond this, monoclinic sulfur melts, transitioning into a liquid. Applying Gibbs rule at these points confirms 0 degrees of freedom, illustrating that temperature and pressure are fixed. Two-component systems contain phase diagrams that represent the interaction of two substances. The lead-silver system phase diagram highlights eutectic behavior. Eutectic point, the lowest temperature where liquid lead and silver coexist. Below this, the alloy separates into solid phases. Liquid region, the area where both components are completely melted. Solid liquid region, contains a mixture of solids and liquid alloys. The eutectic composition allows for a finely dispersed mix of solid phases, important in creating uniform alloys. For better understanding of how it actually looks like, take a look at this diagram. This will help to get on to the concepts easily. In the lead silver system, liquid region. Here, C equals 2, P equals 1, so F equals 2, allowing changes in both temperature and composition. Eutectic point, C equals 2, P equals 3, so F equals 0, making temperature and composition fixed at this point. The zinc-magnesium system features solid solution regions where zinc and magnesium atoms mix in a crystalline structure. Key aspects include: solid solution regions indicate complete mixing at certain compositions. Two-phase region shows equilibrium between solid solution phases of zinc and magnesium. Intermediate compounds. Specific compositions create compounds with unique properties, significant in alloy design. In the zinc-magnesium phase diagram, solid solution regions, zinc and magnesium form single-phase mixtures. Two-phase regions, equilibrium between different solid solutions. Applying Gibbs rule, in single-phase areas C equals 2, P equals 1, F equals 2, allowing temperature and composition changes. In two-phase regions C equals 2, P equals 2, F equals 1, limiting changes to either temperature or composition. Phase diagrams have practical applications in material selection. Engineers use phase behavior to choose materials for specific temperatures and pressures. Alloy design. Metallurgists create alloys with targeted properties by controlling composition and cooling rates. Predicting reactions. Phase diagrams predict which phases will form under specific conditions, essential in fields like polymer blending and ceramics. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.